Hi everyone. This is the third video in our thrilling three-part series of Solids of Revolutions. We're just going to go through and talk about how to solve some problems using the washer method. So even though you know we're going to be using the washer method for every single one of these, I really hope that while you're trying to work on these problems on your own, you just try to recognize why we need to use the washer method. And so remember, just to reiterate, when we look at solids of revolution problems, we want to ask ourselves two things. The first thing is the area or the region that we're rotating in constant contact with the axis of rotation? If it is, we use the disk method. If it's not in contact with the axis of rotation, we use the washer method. The second thing is the axis of rotation aligned parallel to the x-axis, meaning is it horizontal, or is it aligned parallel to the y-axis, meaning is it vertical? If it's the former, we're going to use dx, and if it's the latter, we're going to use dy. So why don't you give this problem a look over and see if you can solve it. Pause the video. Okay, so if you notice, what I like to do with all of these solutions is I like to start out by drawing a picture. So this is what this graph looks like. Here is the graph of y equals x squared plus 1, and this is the graph of y equals negative x plus 3. All right, so the region we're talking about is this region right here. Notice it says we are rotating about the x-axis. So obviously we are rotating about a horizontal line, a line parallel to the x-axis, so we're going to use dx. So the next thing we got to do is we got to find these limits of integration. Well, we can find that by setting x squared plus 1 equal to negative x plus 3. This gives us x squared plus x minus 2 equals 0. We factor that, we'll get x plus 2 times x minus 1 is equal to 0. So that gives us our two limits of integration. This one is 1. That one is negative 2. And so the next thing we got to do is we got to find our inner and outer radius. Remember, the outer radius is the distance of our solid that is furthest away from our axis of rotation. So in this case, our outer radius is going to be that line right there. Well, that's nice. That line is given by negative x plus 3. Our inner radius is going to be this line right here. The inner radius dictates that hole that's in the middle of this solid of revolution. And that line is going to be given by x squared plus 1. So, all right, here's the big time. Let's see if I can plot this one. This one, if we did it in a 3D shape, it would be like that. This guy would come down like here, and then it would go up like that, and then on the inside we would have that, and so that whole area in the middle right there would be a hole. Okay, I think that's pretty good. All right, not my best work, but you get the idea of what the 3D shape would look like in that case. So anyway, if we're going to go ahead and solve this integral, we're just going to plug everything into our washer method formula. So in this case, the volume is going to be the integral from negative 2 to 1. Those are our limits of integration of pi times our outer radius squared. Our outer radius, remember, was negative x plus 3 squared, minus our inner radius, which was x squared plus 1 squared. That, and then dx. In years past, I would have had you guys actually solve that whole integral out. And while that is very good practice, in terms of efficiency, it's not the best. So again, as long as you can get to this particular stage, in my mind, you understand how to come up with the integral. And again, that's the most important thing you got to be doing right now. Okay, so let's try another example. All right, give this one a shot. Pause the video. Okay, so if we look at this one again, I like to graph stuff. So when we graph these things, we have, here is the function y equals x squared, and then coming in hot right here, we have y equals 2x. And so this is the region which we're talking about rotating, but what does it say? It says we're rotating about the y-axis. So since we're rotating about the y-axis, remember that means we're going to be using dy, we're going to be doing y stuff, okay? So what we're going to have to find is, first of all, the y location of that point, so we know what the correct limits of integration are. And then, we're going to have to go from there to find the inner and outer radius. So in order to find what that point is, well, that's going to be a little bit tricky. If we set these two, actually, what am I talking about? It's not tricky. Oh gosh, okay, I'm not even like 2 minutes into this video and everything's already going off the rails. All right, anyway, if we set x squared to be equal to 2x, at x, which I called x squared again, good lord, okay. So if we do this, we get x is equal to 2, so we know that value is equal to 2. Then if we square it, we know this point is going to be 2 comma 4, so that 4 gives us our upper limit of integration in y. And now all we got to do is find our inner and outer radii. So in this case, the outer radius is going to be given by that red line. Well, we got to find that. We have y as a function of x, we need x as a function of y. So if we flip-flop that one, we're going to get x is square root of y, so that's what that outer radius is going to be. Now the inner radius, again, we want to flip-flop this function this time, so x is a function of y, and that gives us x is y over 2. And so now we just apply everything to our Washer method formula. We get the volume will be the integral from 0 to 4. Remember, we're doing all y values here, not x values, of our outer pi times our outer radius squared, square root of y squared, minus our inner radius squared, y over 2 squared dy. And there we go. That's what we're looking for. That's our answer. So again, for practice, maybe try to solve that integral. But for right now, I'm just want to make sure that, again, why do I keep repeating myself on this, by the way? I think this is like the 18th time I've told you guys why we're not evaluating the integral. They get it, Dr. Williams. Stop repeating it. Okay.